and 1D quantum critical systems.
Yes. Thank you. Good morning, everyone. So thank the organizer for giving me the opportunity to talk about entanglement entropy in CFT. We were tasked by Azad to give something rather introductory because the audience is very broad. I'm going to try my best. And maybe the first thing is we've heard in various talks talk about entanglement entropy. So Jia Lins talk about it. Van der Straten mentioned a lot of entropy when talking about tensor networks. And I missed a lot of the talk, unfortunately, so I don't know if actually a simple definition is given. So sorry if it's a repetition. So I'm going to be concerned here with what is called entanglement entropy and more precisely bipartite entanglement entropy. So the setup to consider is a quantum system, is a Hilbert space. You pick a state, psi, in that Hilbert space, and you need to have a Hilbert space of a specific form. It has to be a tensor product, HA tensor HB, and the picture to have in mind is that A and B are two subsystems, and together they form the whole system. So the simplest instance of such a situation is you have two spins, maybe two spin 1/2 A and B. So subsystem A is one spin, subsystem B is the other spin. Each spin has a Hilbert space which is C2, and I'm going to use up and down for my favorite basis of C2. The full Hilbert space is C4, but it's really C2 times C2, and then you can consider all kinds of states in that Hilbert space. And then you can start discussing about either entanglement between A and B or not. So if you consider a state that is a tensor product, you will say there is no entanglement, and if it cannot be written as a tensor product, you will say there's entanglement. That's the first superficial layer. So for instance, if you take up, which is just a shortcut notation for up tensor up, well, of course, that's a product state, there is no entanglement, and then the famous EPR state is entangled. So far, so good. But maybe the first thing to point out is sometimes it's not so easy to see with a naked eye. So if you take this state, for instance, actually it is not entangled, it can be factorized, right? So that's entangled means you cannot factorize your state. Then maybe you want to say a bit more, you want to say how much entanglement there is. So, okay, I'm a physicist, so that means every Hilbert space is finite dimensional, or we can ignore any subtlety if that's not the case. So let me pick an orthonormal basis EI of HA and FJ of HB. And an arbitrary state in the tensor product is going to look like this kind of linear combination, and Aij is some rectangular matrix, complex entries. And if I do a singular value decomposition of this matrix, I end up with this kind of decomposition. It's called the Schmidt decomposition in this context of psi with respect to a certain bipartition. So I went from a single to a double sum to a single sum, and it's not just relabeling, because now my new state Uj, they're all mutually orthogonal, and the Vj also are orthogonal. And the Pj are non-negative numbers, and they sum to 1. So there is some freedom, especially if the Pj's have degeneracies. This is not unique, this decomposition, but what is well defined is an integer here, called the Schmidt rank. It's a number of non-zero singular values of the matrix A. And the actual value of the Pj, the singular values, is also well defined. So if there is no entanglement when there is a single sum here, when R equals 1, Schmidt rank is 1, it's no entanglement, and when it's larger than 1, it's entanglement, right? So now we want to introduce, oh yeah, not right now, but soon we will introduce measures of entanglement. We won't say how much entanglement there is, but we're slowly going there. One thing I want to talk about is the notion of density matrix for people that are not familiar with it. So when you do quantum mechanics, you can either work with a pure state, so it's a state of the Hilbert space, or you can work with a statistical superposition of states. Then you describe your system by what is called a density matrix. So for instance, such a density matrix would describe a system, a quantum system, which is in state psi j with probability pj. So the sum of the pj has to be 1, and this is the orthogonal projector onto psi j. So rho is essentially any Hermitian trace 1 positive, that's it, operator in my unit space. That's a general density matrix. And so this notion of density matrix is very convenient to describe what happens to a subsystem starting from X. So if you start from a full system in a state rho and you have a bipartition, then it turns out the small system is described by a reduced density matrix. So it's a density matrix, we call it reduced because it's for the small system, which is obtained by tracing rho over HB. So as far as any measurement, so as far as A is concerned, the subsystem A is just described by this rho A. So you can forget about everything. So you start from your big rho, you trace over B, and that describes your small system. So what's the connection with the Schmidt decomposition? Actually, is fairly straightforward. Once you've done the Schmidt decomposition, it's very easy to trace over B, and you realize that your rho A is now going to be diagonal. So the uj, there's the eigenstates of rho A, and the pj, it's the eigenvalues. And it's trace one, so the sum of the pj is one. So the physical interpretation of this is that you start from, even if you start from a pure state psi, you do the Schmidt decomposition. Now your subsystem A is typically no longer in a pure state. It's in a statistical superposition of states. It's in the state uj with probability pj. If there's no entanglement, in fact, it's still deterministic. It's a pure state, but if there was entanglement, then now it's no longer a pure state. So having said that, now we have so the PJ is really a probability distribution. So what you can define now, if you want to talk about entropy, is just take the Shannon entropy of this distribution. And that's in that context that you define what is known as a von Neumann entanglement entropy of your quantum state. So it depends on two things. It depends on the state you're in, and it depends on a certain bipartition of your Hilbert space. And it has all kind of nice properties. So it's non-negative, and this entropy is zero if and only if there's no entanglement. The entropy of subsystem A is the same as the entropy of subsystem B, starting from pure states. And there's some other nice property. One of them is strong subadditivity. So if you take two subdomain A1 and A2, you can look at the entropy of the union plus the entropy of the intersection, and that's going to be less or equal to the entropy of A1 plus the entropy of A2. So that's a measure of entanglement, but you can introduce various ones, and the ones I'm going to be more concerned about are this Renyi entropy of order n. So here there's an extra parameter which is n, and essentially you take sum of pj to the n, so that trace of rho A to the n. If you want, take the log, divide by 1 minus n. Why do we introduce this one? Well, these ones are going to turn out to be easier to compute. And if by some miracle you manage to compute this for any n, and you analytically continue to n equals 1, you recover that one. Right? Any questions? Good. Okay. So I'm not going to look at entanglement entropy like in a two-spin system or in an arbitrary. Typically, I'm a low-energy physicist, so I care about a many-body quantum system, so lots and lots of spins of some other microscopic degrees of freedom, and at low energy. So typically a ground state or low-lying energy states or small temperature. And why do we care about entanglement entropy? So first of all, well, it's a resource for quantum computation. If there's no entanglement, you can't do anything. We heard from the talks about tensor networks that actually understanding the fine structure of entanglement in your quantum state is very useful when you want to simulate them on a classical computer. All these tensor network methods rely on this. And me, I would be more like here, I'm a theorist, so we use entanglement entropy as a probe for what kind of phase of matter you have. So for instance, in one dimension, if you have a gapped system or a gapless system, the entropy is going to behave in a very different way. So by looking at the entropy, you can detect whether it's gapped or not. And when it's gapless, you can extract all kinds of information like the central charge, etc. And there's some analog in higher dimension, which I'm not going to talk about, but for people that know, if you have a two-dimensional gap phase, entanglement entropy will detect whether you have anions in your system, so whether you have topological order. So essentially, that's a theorist probe for the kind of low energy properties of your phase of matter. And I think a theorist probe because it's actually experimentally it's completely inaccessible. It's not something you can actually measure, or people are trying, but we're very, very far from it. It's not a local measurement, it's really a global property of the system. So the kind of things we're going to look at is we're going to look at spatial bipartition, which is where A and B correspond to two spatial regions. You could divide the system in all kinds of ways, but it's interesting to do really spatial. So for instance, if you have particles on some manifold, you're going to say A corresponds to some domain and B is a complement, and you're going to look at the Hilbert space split in that way. And the case where A and B contains a very large number of degrees of freedom, and the system is in the ground state, maybe a low-lying excited state or finite temperature, small energy. So there's been observed a very broadly applicable behavior of the entanglement entropies. It's not a proof, but in all the systems we can think of, this is essentially true. If you have a system that is gapped, so that means there's a finite correlation and in any dimension, and you look at so let's suppose we work in R to the D, so and you pick a finite domain A, and you pick the ground state of a local gap Hamiltonian, and you look at the entanglement entropy of A with respect to B. And then you can ask, how will this entanglement entropy grow as my region A is rescaled, is dilated? And the statement is that it's typically not going to grow like the volume of A, it's rather going to grow like the volume of the boundary of A. So it's called the area law in 3 dimensions, but in fact, then it's called the area law in any dimension, but it really means that the entanglement entropy grows like the size of the interface between A and B. So it's not extensive, at least at 0 temperature. If you know at finite temperature, it's different, but at 0 temperature, that's what's been observed. So there's some proof in 1D or some specific lattice model with all kind of assumption about the kind of range of the interactions, and in higher dimension, we just observe that it seems to be always true for gapped system. Now, what happens if you have non-gapped system? Then, well, it turns out if you're in dimension at least 2 spatial dimensions, so 2 + 1 and above, often you still have the area law, but not always. For instance, one counterexample is if you have a Fermi sea or a metal, so let's say free fermion, but that's not very precise. Really, it's you take your Schrödinger p²/2, like a Laplacian, and you fill your state up to a certain energy. You have a big Fermi sea with a big Fermi surface, and you're going to have a log enhancement of the area law. So it's not going to grow like the size of the boundary. There's going to be an extra log of the size. So it grows a bit more. And another famous class of counterexample is in 1 dimension. So that's what I'm going to be focusing on, is 1-dimensional critical system. So in 1 dimension, well, the boundary of a subsystem A is just 2 points. So you can take A as large as you want. Boundary doesn't change size. So if you have the area law, what you'd find is for a gap system, if you were to compute the entropy in that setup with a single interval as a size of as a function of the size of the interval, it would grow and typically saturate to a constant. Because the area law tells you it cannot grow faster than constant. So it goes asymptotically to a constant as the size of the interval becomes big. But when you're critical, you don't find this. You find that actually it grows forever. And it grows as C/3 log of the size of A, at least for a single interval. So you have these Helland's entanglement entropies. That's how you here distinguish between gapped system and gapless systems in 1D. And furthermore, what's very interesting is that the prefactor is universal. It gives you the central charge. So if you take 2 completely different lattice models that are critical, but they're in the same universality class, you will have the same growth of the entanglement entropy. It's universal in that sense. Right. Okay, so now, so for those of you that attended the talk of Jiasheng, he was motivated by entanglement entropy, but he was talking about partition function on branch cover of CFT. So maybe now my next objective is to take you from the basic definition that was given to how do you end up on branch cover and CFT. All right, so maybe let's take to have something very concrete, the quantum Ising chain at criticality. That's a quantum Hamiltonian. So it's a, I took here a finite chain on a circle with L sides. Right, so that's my spin chain. So every vertex I have a spin 1/2, and I put this Hamiltonian on. So the first thing is to go to the Euclidean picture. It's going to be more convenient. So rather than working with a quantum system, I'm going to work with a classical Ising model. Now on a 2D classical graph. And the point is, if you look at the transfer matrix of the Ising model, so it's going to be now an Ising model on an infinitely long cylinder, if I want the ground state. And here is just a slice of my cylinder. And the transfer matrix, it what takes you from a row configuration to the next row configuration. it's an explicit symmetric matrix, which essentially every time you act with T, you add one layer to your cylinder and you implement all the correct Boltzmann weights. So the Boltzmann weights are included here. So you're gonna need to add the Ising interaction for vertical edges, which is included here. And then you need to add the blue ones. And well, there's a square root because for instance, this blue link is gonna appear when I act with T, is gonna be there again when I act with the next T. So I can have twice the square root, I'm gonna have the full Boltzmann. There's other ways to write a transfer matrix, but in this way it's symmetric, so it's kind of more convenient. Anyhow, so you have this transfer matrix, and the fact is, the largest eigenvalue, the largest eigenstate of this transfer matrix is exactly the ground state of this Hamiltonian here. So rather, if you want to construct the ground state of this Hamiltonian, you can look at the largest eigenstate of this transfer matrix. It's the same thing for any system size. So then there's a simple rule to build a ground state. In quantum mechanics, you would say, I start from essentially any state that is not orthogonal to the ground state, and I act with the imaginary time evolution for a very long time that's going to project onto the ground state. That's very easy. So the analog on the lattice is to start from essentially any state and act with the transfer matrix many, many times. Oh, sorry, that should not be it's not the same L as the system size. Should take another L. And so here, lambda naught is the largest eigenvalue of the transfer matrix. So picturally, that means you're working on you act with the transfer matrix infinitely many times. So what you have is an semi-infinite cylinder, but you can embed on the unit disk like this. And the quantum state is living on the outside. So if you want, it's some kind of Segel amplitude, but on the lattice, you associate to a disk a state. And if you don't want the ground state, but some excited state, you just need to, it's easy, you just need here to put a state that's orthogonal to the ground state, and then you get some excited state. You can build all the states. Right, so to be more specific, what I mean is, if you want the ground state of your quantum Ising chain that you can decompose into, so here the S's, there would be this up or down arrow, or in the Ising model, it's plus and minus. So you're gonna have 2 to the L coefficients on your Hilbert space. And each coefficient is given by a partition function of the Ising, classical Ising, on a semi-infinite cylinder in which you fixed the outside configuration to be, well, the configuration you want. So that's what I mean by the kind of lattice segment amplitude. Right? That's just a recipe to cook up the ground state. And I showed you for Ising, but you can do it for essentially any integrable chain. You can play the same game. Okay, so now that we have this, let's see how to get the transfer matrix. So first, we're going to build the projector on top psi naught. So you do a first, if you want, lattice amplitude to get psi naught, and you do another one to get the dual here. So this, as an amplitude, is if it's a projector onto the ground state, and then you trace over A. That's how you build the reduced density matrix. But in that language, tracing over A is very easy. So let's suppose A is this region here, from here to there. A is here, is the part where I don't trace, and B is this part of the chain. So maybe see, roughly that would be B, and this would be A on my chain, or if I have a single interval. The trace is very easy. In fact, it simply amounts to saying, in this partition function, I must force this spin to be equal to that spin, this spin to be equal to that spin. So if you want all the red links, they're just Kronecker delta functions. Force the links to be equal. So that is a reduced density matrix. So again, to make it more specific what this is, so I made a little zoom on my cylinder. So from below was, I have an infinite cylinder also on top. And on this part, I've traced, well, that's the region B, and in the middle, where I have the slit open, it's A. And so the claim is the matrix element of rho A, which are labeled by configurations living in HA here and here. So each matrix element of rho A is again a partition function in which you fix these values to be equal to these guys, and you fix the top to be equal to that. So if you want, it's again a kind of a Segel amplitude. You fix the boundaries. All right. So once we have this, we can do trace of row A to the n. So each, and that gets us immediately to branch cover. So should think of this lattice. So such a thing, such an operator now is in each sheet, and the trace amounts to identifying. So when you multiply, when you do row A squared, essentially you're going to force this configuration here. It's the bottom of the slit on the lowest sheet. It's the bottom of this slit. Sorry, you're going to have to identify it with that slit here on the second slit. That's trace of row A squared. Sorry, row A squared. Then you identify it. So the trace, if you want, connects your different sheets cyclically, and then you trace at the end. So that means that trace of row A to the n is literally the partition function of an Ising model just embedded on that surface. For any size, so that's an exact, there is no approximation, no weird limit. So that's, you take a quantum Ising chain with L sites, and you want the entanglement entropy, it's exactly equal to the partition function on that thing. There's just one thing I cheated about. You have to be careful about normalization. So I didn't cheat, but it's very mild. You have to divide by this just to ensure that trace of row A is 1. So in that picture, maybe I should have said, that is not actually row A is proportional to row A. If you take care of all the normalization, you need in particular that trace of row A is 1. But how do you trace this guy where you say this is equal to this and I sum, this is equal to this and I sum, so you close the slit. Tracing is just closing the slit here. Trace has to be 1, so that means in fact the correct amplitude is this divided by the closed partition function. So when you do trace of row A to the n, well, you have the partition function to the n. It's just normalization. So, and so far we're still on, there's no CFT, we're still on the lattice. We're looking at lattice partition functions, and it's exact. All right. So then you're going to say, well, it's a critical system, so I should be able to describe any partition function with conformophilia. And the standard ansatz for the scaling property of a, so that would be a lattice partition function. It depends on some lattice spacing A. When I send A to 0, I go to the continuum limit. So there's going to be some non-universal amplitude, which is proportional to the area. This one I can't predict with CFT. It's non-universal, but the next term is universal, and it's a partition function, the CFT partition function. That's the one we kind of, this part will be able to compute with CFT. And then there are subleading corrections, which in fact you can also compute with CFT up to some amplitude that you need to fix. So now when we look at partition, the ratio of partition function of the kind, that one here, if you think about it, the area of the cover is n times the area of the base. So in fact, that non-universal piece just cancelled out exactly. And you're left just with this goes as A goes to 0 to the CFT ratio of correlation. So that means the entanglement entropy of the Ising chain is equal to a ratio of CFT correlation function up to stuff that goes to 0 as a lattice spacing closed. So there are finite size correction that you can compute, but there's a leading term which is just a ratio of CFT partition. So that's a super short summary of Jiashank's talk in the first week, for those of you that didn't attend. So if you want to consider partition function of the branch cover, you have a little issue is that at the branch point, you have conical singularities. So the metric is singular at the branch point. So you need to regularize this. There's a natural way to do it by removing balls of size epsilon and then see what happens when epsilon goes to 0, putting the right count term. So you can make sense of these partition functions on surfaces with conical singularity. And maybe the most interesting property, okay, they were defined fine, but what's interesting is if you take such a ratio and you do a veil rescaling of the metric, what happens? Well, something very simple happens. You just pick, so the rescaling of the metric, this is only sensitive to the rescaling of the metric at the branch points. So the xj here are all the branch points. And it looks, so for those of you that are familiar with CFTs, this looks exactly, this would be the same behavior for a correlation function of primary fields. It looks exactly the same. If it was a correlation of function of primary field, we would call delta j the scaling dimension of the primary field, if you want, of the conical singularity. But this behaves exactly like a correlation function. And you can compute this dimension here, so they depend on the kind of branch cover, but the case we're interested in is cyclic cover. So you need to go n times around each point to go back to the initial point. In that case, the dimension is simple, it's proportional to central charge, and then n times minus 1 of n is the number of sheets, it's a Renyi index. Okay, so once we have this, there's a simple, very easy calculation to do is, well, what happens to my Ising chain here? Or maybe to make it even simpler, I can take an Ising chain defined on the whole real line and take A to be a single interval. So change again. So I'm going to take an Ising chain that's on the full real line, and I'm going to take a region A that is made of L sides. Not L sides, size L. So the number of sides here is going to become very large as my lattice spacing goes to 0. Well, when A goes to 0, I'm going to end up with a partition function, or what is it? So I'm on C because I have an infinite line and I put Euclidean time I want the ground state. So the base would be C, so it would be exactly like this picture here. Actually, there will be exactly this branch cover here. It's C or CP1 if you compactify with two branch points. So why is this easy? That's because the cover, sigma n, the branch cover, still is a sphere. Topologically, it's a sphere. That's easy. There is no modular. So all you have to do is deal with the conical singularities. That's fine. And you end up with something very simple, is dealing with the conical singularities. This ratio is L to, well, this is just 4 times the delta J we had above. So that leads to the famous Calabrese-Cardy formula that if you have a conformal field theory, you put it to a quantum system on the real line and you want the entanglement entropy of a single interval in the scaling limit, that's going to be C over 6, 1 plus 1 over n log L. So that's it. So okay, so now we're done. We know how to compute all entanglement entropies in 1D. Well, in fact, no. This case is easy when it's a single interval. So when do we have trouble? Well, what happens if you take 2 intervals? So now let's change a little bit our picture and say A is the disjoint union of 2 intervals. Well, now, if you think in terms of this, let's make our life easy still and take n equals 2. So you have to take a 2-sheeted cover of CP1 with 4 branch points. So that's this curve here. So why is that more complicated? It's because now the cover is no longer a sphere, it's a torus, topologically. So now you have to worry about if it's a torus, like what's the moduli of the torus. So here it's not very hard to compute. I mean, it's easy to write. There's only one non-zero holomorphic form here. You integrate it over the cycles. You get some hypergeometric function. You get your modular parameter explicitly as a function of x. So here I've used Mobius maps to send my my branch point to 0, 1, x, and infinity. So there's only one parameter, it's x. So x, if you want, would be the cross ratio of all the 4 ends of your interval. So here what you find is that this ratio of partition function, so there's a piece that comes from regularizing the conical singularity, but you're still left with something complicated, which is a torus partition function. That's different for each CFT. So that's very different from this result. In essentially, any CFT, only the central charge matters. So 1 interval is very simple. 2 interval, n equals 2 is already much more involved. You have the torus partition function. But that's still fine because the torus partition function is well understood. Like for minimal model, we know how to compute this, it's fine. What happens if you increase n? So now we still have 4 branch points, but now it's an n-sheeted cover. Well, now this has genus n minus 1. So the modular space is huge, but still you can compute it explicitly. So you can write down the n minus 1 linearly independent holomorphic forms, integrate over the cycles, and you get some explicit formula for the period matrix, which is made of hypergeometric function. You say, good, fine, then I know how to compute it. Well, Yes and no, because what you're going to find is your entanglement entropy ends up being related to a particular partition function of genus n-1. You know the moduli, but how to compute this partition function actually is not that simple. So it's like not super helpful, except if it's a very simple theory, like a compact GFF or if it's a free theory, essentially, you know how to compute these things. Otherwise, not so useful. And this kind of problem you encounter, so I was talking about the ground state entropy with 2 intervals, but if you work on even with 1 interval, you can have issues. If you, for instance, you consider the Ising's chain with periodic boundary conditions, so it's on a circle, and you put it at finite temperature, then the Euclidean spacetime is already a torus before you do the covering space. So now you have to look at branch cover of a torus with 2 points, 2 branch points, and the genus is n. So you have the same problem that you're going to have to work in high genus. In fact, in that case, the period matrix you can still compute, but it's even more horrible because instead of integrating holomorphic form that are just z to some powers, they look like Selbel integral. Here, they're going to be theta functions everywhere. I mean, it's a bit of a mess, but you can still write down the period matrix. But still, you have the problem that at the end of the day, how do I evaluate the partition function in genus n? For instance, I take the 3-state Potts model, but I don't know how to do that. Okay. Maybe another case when life is difficult is if you start considering systems with boundaries. So now let's take, for instance, the Ising chain again, but we don't put periodic boundary condition, we put 2 conformally invariant boundaries. So for Ising, there are 3 such boundary conditions. So all the spins are plus, it's frozen, or they're minus, or it's free, like open. There's 3 boundary conditions, they're classified. So I label my boundary condition by alpha. So to make our life easy, I'm going to put the same boundary condition on both sides. See that it matters if you don't put the same boundary condition, it's much more tricky. And I'm going to consider a single interval here in the middle. And I'm going to take again n equals 2, only 2 sheets. That's the easiest Renyi entropy I can compute. Okay, and at 0 temperature. So before doing the cover, if you want to construct the ground state of this, well, you have to put it on a strip. So you do a transfer matrix, but with open boundary condition this time, and you work on an infinite strip. If you compactify, it's a disk. So you work on the unit disk, and at the boundary of the disk, you put the conformal boundary condition alpha. So what you have to look at now, the branch cover is a disk with 2 punctures, and there's 2 sheets. So there's an easy way to see what kind of topology you get is where if you take n sheets and you end up with n connected component for your boundary. So if I were doing n sheets, I would get essentially it's a sphere with n disks removed. That's the kind of object you have to look at. In principle, that's hard, but if I take n equals 2, that's easy because that's just an annulus. And the annulus partition function is like the torus one, it's well tabulated, it's easy to compute. So you can play the same game here and relate it to the annulus partition function, and this case is fine. But as soon as you increase n, you're in trouble. So, right. And there's all kind of cases you can consider. You can, if you don't want the ground state, but some excited state, it's going to be more complicated because on top of, well, in terms of that Segel amplitude, you're going to have to insert a field in the middle of your disk. So now it's no longer be partition functions. You're looking at the partition function with field insertion. So it gets also more complicated. If you put systems with different conformal boundary condition on both hands, like here, but imagine you put some boundary condition for using like plus and here minus, what changes? Well, it changes that if you compactify and put it on the disk, you have a disk with 2 different, half of the boundary is plus, the other one is minus, so you have to introduce boundary condition changing operators. So again, that means field insertion. It's also more complicated. And there's a whole other game to look at symmetry results, entanglement entropy. I can just say in 2 words, but if you have an extra symmetry, like maybe when Ising you have a Z2 symmetry, there's a way to define a refined notion of entanglement that takes into account this symmetry, and you can encode here by modifying the partition function. So there's all kind of situation that I think are actually pretty hard to compute. Okay, so it turns out in this geometric approach, when you look at partition function on branch cover, there is a big price to pay. Is typically you end up working on surfaces that have a very large moduli space for no good reason, because if I'm in that situation and I look at the nth ready entropy, I'm in genus n-1, but secretly my moduli space here is only one-dimensional. So I'm kind of suffering for no good reason, because I have to write this, what is a period matrix in terms of a single variable, which is x. So I don't care about the partition function on genus n-1. In general, I just need for a precise curve in the moduli space. So maybe there's a simpler way to do this. And one kind of way is to look at things differently and go to the cyclic orbifold picture. So I'm going to introduce this. And starting from the lattice before talking about CFT. And if you take the same picture of before as a reduced density matrix between, it's essentially a partition function where you cut open here and these sides are free. And then you do trace of row A to the n. So you'd imagine you have your Ising model on the n sheets. And whenever you go around the branch point, you move to the next sheet. That's one way to look at it. That was a geometric way of doing. But maybe you could say, I don't want to work on this cover. I'm going to squash all my sheets together. So now the base, I'm just on the plane. What's the difference is now that each side, I don't have one Ising spin, I have n of them. You collapse them. So your lattice model is more complicated, but in fact, if I look at what is the interaction here for Ising, it's just going to be, well, all the different layers of the Ising are not going to talk to each other. There's going to be just a product of the previous interaction. So A here is what used to be the layer index. So what's going to be modified is only these red interactions. So across the red interaction, the spin A will talk to spin A plus 1 here of the Ising. Okay. So you just modify, essentially you start with Ising, you take n copies, and you allow these kind of defect lines through which the Boltzmann weights are modified. That's completely equivalent to the other picture. It's just rewriting things. So for people that are familiar, for instance, with the Khatanov-Seva disorder operators, it's exactly the same kind of constructions. You introduce a defect line and then you modify the Boltzmann weights. These are called disorder operators in the context of Ising with a disorder line. And in that context, they're called twist fields. In fact, it's a more general construction. If you take any lattice model in which you have a global group G acting, you can always introduce defect lines and twist and essentially modify the interaction by adding with a group on only one of the copies. So here, what is a symmetry group where we have n copies of Ising initially? So there's a big symmetry which is just permuting all the copies. It's a permutation. But here we don't really care about this complicated group because of the kind of cover we have. We just care about cyclic permutation, so a Zn abelian group. And this is the kind of defects we're implementing. Okay, so on the lattice, this is well defined. And very much like in Ising, we're going to assume that in the continuum, this is described by some kind of conformal field theory. And in Ising, we know what this becomes. In the disorder operator. So at the end of every such line, you end up with a field. So why only at the end? Because, okay, I'm maybe not going to do the full argument, but essentially you can convince yourself that where this string is sitting, it doesn't matter. You can just move it, you can deform it continuously. There's no problem. So the only thing that matters is where the end of the strings are sitting. That's where the operators are. And so you have to allow, so the idea will be to take n copies of the conformal field theory and allow such defects inside. And well, via the state operator correspondence, it means the Hilbert space will also have some twisted sector, which essentially is the kind of amplitude. Say you want to do you cut around the twist field and you look at the kind of single amplitude you have. It's going to be what's called the twisted sector. The Hilbert space is going to be the twisted sector. So with this picture, we have traded our conical singularities, our geometric defects, to kind of algebraic defects. This twist operator stuff. And now instead of computing this kind of ratio of correlation function, we have to compute, partition function, we have to compute a correlation function of twist fields. For instance, in that picture here, it would be a 4-point function of twist field on CP1. So the gain is that this is the right moduli from the start. You don't have to worry about having a huge period matrix. It's just you put this one to 0, 1, x infinity, and it only depends on x. And this picture also enlightens something that we've said before. I said, well, strangely, this ratio of correlation function behaves exactly like the correlation function of primary fields, because it is secretly a correlation function of primary fields. Once you move to the orbifold pictures, this becomes very clear why that's true, because this object, it has to behave in a certain way. And by the way, that means we already know the conformal, the scaling dimension of these guys. All right. So now I have to describe the kind of conformal field theory we have to deal with when doing this picture. So we started from n copies. I'm going to call the mother theory the Ising, for instance, CFT in that case. And I've copied n times. And then I have to, so naively, the fields are going to be just multiplets. And in particular, I'm going to have n copies of the stress tensor, one per Ising, CFT. But in fact, now in that picture, they lose most of the geometric meaning, because I only have the full stress tensor, which is the sum of all these guys. This one has geometric meaning. That's the one that will couple to deforming my surface. And I have, well, it's going to be convenient to actually do a discrete Fourier transform of these guys. So, well, essentially, because these are the objects that are going to have a well-defined monodromy as you go around branch. And the t hat 0 is just a sum of all the stress tensor. That is a true stress tensor of this orbifold. And all the other ones, you could think of them as extra currents that don't really have a clear geometric meaning. So it's kind of a W algebra. You have a big extended symmetry. But the commutation relations are pretty simple. You just have this extra Fourier index that's just additive. Simple enough. At least when you're working in the untwisted Hilbert space, that means when you do you're looking at Segal amplitude with no twist inserted inside. In the untwisted sector, that's very simple. So when I say fields are this, really, I'm talking about the untwisted sector. So there's also a twisted sector. That means if you do Segal amplitude around a twist, and the Hilbert space now is quite different. And the first thing is maybe to say is that if I take these extra currents, they're no longer single valued, because if I take them around the branch, but I get a phase. I mean, if I do the Lorentz series, they're still holomorphic, I get fractional modes. So all these extra current, they're a bit weird that in the twisted sector, they no longer have integer modes like Virasoro, they have fractional modes. But the algebra is still the same as above. It's still this, but now n and m, they're actually not integer. And what's funny is that there's a way to relate, to express these fractional modes of these extra currents to normal Virasoro ones. How does that work? Is, well, suppose you do a Segal amplitude around the twist. Well, secretly the disk, I can unfold it, and it's just a disk in the mother theory. So you can map this amplitude to an amplitude in the unreplicated CFT. Via just a map z equals w to the n, you unfold everything. And if you see how your stress tensor is going to change under this, you realize that your new modes of all your new currents are just related to the modes of the stress tensor of the mother theory. And u can be fractional, but nu is integer, so it's fine. And there's an extra piece that comes out from the Schwarzschild derivative, and surprise, surprise, it's just the scaling dimension of the twist field. Everything comes in together. And this is very nice because essentially what this is saying, and I think that's was realized already a long time ago, of Alprin and Schweigert, that it means that the Hilbert space in the twisted sector of the orbifold is isomorphic to the Hilbert space of the mode theory. There's the same Hilbert spaces, except that the Virasoro action is different. In one case, it acts by these guys, in that case, it acts here. But maybe I'm just going to enter into the detail. What's the most important part is if you have any null vector in the mother theory, translate immediately into null vectors in the twisted sector. So there's a map from the Hilbert space of the mother theory to the twisted sector of the orbifolds for induction. And now it's very nice because you can say, well, if I want to compute a correlation function of 4 twist field, as long as my mother theory is rational and I have null vectors, I'm going to have null vectors here too, and maybe I can get a differential equation and then therefore compute all my conformal blocks in this way. And turns out in some cases you can. So let's take a very concrete example. Take the simplest minimal model, which is the Yang-Lee, well, besides C equals 0, that is nothing, but first non-trivial one. The Yang-Lee CFT, it has two primary fields, 1 and 5. It's conformal dimension, I don't remember, when 1 is 0, but 5 is negative, it's non-unitary. And the vacuum of the identity has two null vectors. There's a standard one that L-1 yields it, and there's another one at level 4. When you do induction, you realize that means immediately that you twist fields. So I'm doing induction for n equals 2. So I take 2 copies and I have 4 defects. The twist field is going to have two null vectors. It's going to be this one, which is always there because it's the analog of that one. So the interesting one is this. It turns into that. So this looks very much like a phi 1,2 state. And in fact, as soon as you have this, there's a standard recipe to derive an ODE for the 4-point primary fields, which is function over the 2, and the solutions, it's here. The solutions are upper geometric functions. These are the two conformal blocks for Yang-Lee. And then you can play the game of doing the bootstrap, like you demand crossing symmetry that fixes everything. You end up with an explicit 2-point function for your twist. Well, but actually here I'm in a situation where I already said that this one we already knew. It's essentially the torus partition function. How do you reconcile the two pictures? Well, it turns out that these two things are exactly the characters of Yang-Lee. So this is nothing. If you change variable from z to tau here, on you recover really, it is the torus partition function. You just derive it in a different way. So here you don't really gain anything. But if you start going to, if you manage to make this story work for n equals 3, 4, etc., then you get. You can play the same game for Ising, and maybe I'll show you. So I can spoil. You're going to just recover the Ising model on the torus, so you get nothing. But just to illustrate the kind of difficulty you get when going with this picture. So Ising CFT, the identity or vacuum has two null vectors, the usual one at level 1, and now a more complicated one at level 6. So it's still n equals 2. I do my induction, I get the trivial one, and then I get another one here at level 3. But here we have a problem, is we have one of these fractional modes. And all the black ones are good because they come from the true stress sensors. They act geometrically, which means in correlation function, they're going to act as differential operator. That's fine. This one does not act as a differential operator. So you need to get rid of. It's a standard problem when you have extended symmetries. It's not just Virasoro modes. It's not because you have a null vector that you immediately get the differential equation. You have to work a little bit extra. But you can in that case, and you get node 3 differential equation and the solution. Yeah, there's the concept. So maybe let's conclude with because so far I showed you cases in which we recovered torus, so we don't really gain much. Maybe let me show you a case in which we get something new. So we're going to again take a system with on an open chain with 2 boundary conditions, and this time I'm going to pick the boundary condition to be different, alpha and beta. And I'm going to put a single twist. That's a bit easier. And what does it map to into my picture of twist fields? I'm going to have a single twist field on the unit disk, but because I have 2 different boundary conditions, I'm going to have 2 boundary condition changing operators. So it's a correlation function on the unit disk or the upper half plane, if you prefer, with 1 twist in the bulk, 2 BCCOs in the boundary. Yeah, which are represented here. So if you want, it's an upper half plane. Right here. So it's here, upper half plane. I have a twist somewhere, but I have boundary condition alpha on one side and beta on the other, which means here there's a boundary changing operator. So there's one case that's easy, and that was done already in the first papers of Calabrese and Cardis. If alpha equals beta, then in fact there is no boundary condition changing operator. It's just a 1-point function on the disk, which is trivial to compute, and you get the entropy straight away, and it only depends on the central charge. And there's one other thing coming up. The G alpha is a Ludwig-Affleck boundary entropy, or if you want, it's a partition function of a disk with nothing inserted and boundary condition alpha on the boundary. But what happens if alpha is different from beta? Well, generically, we don't know the answer. We don't know what the entanglement entropy is. The one thing you can say is just because it's a one-point function on the upper half plane with BCCOs, it has to be of that form. There's a piece that is the same as above. But instead of that simple log G alpha, what you have here is some scaling function of little l over big L. So little l is the size of the interval, L is a full system size. This is a universal function. It should be computable by CFT, but typically we don't know what it is. All we can say is it interpolates between this value when L goes to 0, and when L goes to big L, it has to be log G. So one case when you can compute it is if you choose your boundary condition in such a way that the boundary changing condition operator is degenerate at level 2. So this appears in all kinds of setups. It's not generic, but it's not uncommon. For instance, for easing, you can take what you want here and here, you will always have that. So if you have a null vector for this guy, you can play with that machinery of trying to get all these. It's not straightforward. So we really have to do it case by case. For n equals 2, you have to work. For n equals 3, you have to work. For n equals 4, we still have to work. We don't know how to do it. So as you increase n, this gets more and more complicated, but it's just an algebraic difficulty. There's nothing geometric. For instance, for n equals 3, you get some differential equation, function of order 3. This coefficient, they depend on G, which is the parameter here. So they depend on the central charge if you want secretly. And this gives you a good handle on the conformal block. So you don't have a nice expression in terms of hypergeometric, but you can write an explicit series. You can use a Frobenius method to generate power series for your blocks and then solve the bootstrap, and that allows you to compute this correlation function. So okay, that was another example. And by conclusion, it was a bit of an overview of, well, a very personal overview of entanglement entropy in 1D quantum systems. So I presented this kind of two different approaches you can do, which are complementary. One is more geometric, in which you have to deal with partition function on branch cover. But the difficulty with this is that somehow you have to work with a very large modular space for no good reason. And then you have this more algebraic approach, which is a cyclic orbifold. And provided your CFT is rational, there's hope that if the mother theory, the CFT is rational, the orbifold you build out of it is also rational. That's automatic. So you have null vectors, but that doesn't mean it's easy to get differential equation out of it. Presumably, but there's a whole kind of algebraic difficulties to make it work. So in practice, we make this for we play this game for n equals 2 and 3, and that's it. So now there's a kind of a third route maybe that would be interesting, and people look at it. So I called it looking at entanglement Hamiltonian. But really what this means, going back, is trying to understand the reduced density matrix itself as a Segel amplitude. It's a bit of a weird Segel amplitude because well, essentially it's a sphere with the in state is not on a circle, it's on an interval, and the out state is here, also on an interval. They include, and there's angle 2 pi. So this is a Segel reduced density matrix. And maybe if this was well understood, you could say more things directly at that level, but that's a question for the future. And that's it. Thank you. Any questions for Benoit?
So if you look at that you're computing, for example, a 4-point correlation function on a replicated CFT with insertion of 4 primary operators. If the replicated CFT is a minimal model, so this 4-point correlation function, do you think is satisfies all this? I mean, if I look to his spectral to his factorization of this 4-point correlation function, do you think it will be always on a finite spec on a finite?
You mean
yes.
this?
Yeah.
Yeah, we know we know the blocks. We know the dimension of everything.
Because
how
it
many
is a
there are.
minimum model.
So there's finitely many blocks. So there should always be an ODE, I guess. But
Even if like this, first I get confused. Even if this twist operator are not degenerate. I mean,
but then they are. If you start from a rational CFT, they are always degenerate.
Okay. The twist.
If you, as long as the model theory is rational, then also that. Well, except I drew this, but it's not Virasoro conformal block. They're extended blocks. You know. Yeah.
So do all CFT have orbifold version or only certain CFT?
I mean, the physicist answer is everything exists. So a priori, I mean, I don't see why not. But
you need the extra symmetries of your Lagrangian or something to have.
Yeah, even if they have extra, yeah. In fact, the paper I was mentioning,
But I mean, without.
so this paper here, they deal with all kind of extended symmetries and by zooming Witten. They do the systematically, if you want.
I was asking if your Lagrangian doesn't have special symmetry, you still expect to have an orbifold version.
Oh, you mean more general? Okay, so not this kind of orbifold, more generally. But the only kind I know is you have to have some group acting on your CFT, and you can turn in some orbifolding, that means inserting these defects. But if you don't have any symmetry, I don't know what kind of defects to introduce.
And in which case do you have these groups?
So the particular case I'm dealing with, you start from a CFT and you replicate it. So then you have permutation symmetry automatically. But there's other cases, if you have a GFF, you can change, you have a Z2 symmetry, which is phi to minus phi, because that's your original orbifold in string theory. Or if you have a compact GFF, you can just turn them. I mean, they live on a circle, so you can shift them by. There's all kind of setup. In Ising, you have a Z2 symmetry. In the three-state post model, you have a S3 permutation. But it's really depends on the CFT you look at. It's kind of a machinery to generate new.
But you're saying that you can always do this replication.
But I can always take a tensor product of two CFT and.
But it's not just tensor product, right? Because they sort of interacts with the defect.
Yes,
right?
yes.
It's not just because you understand correctly. Your enfold Virasoro. It's not just product of Virasoro.
No, it's not.
They talk to each other just because of this defect.
Yes,
Defect,
yes.
right? So this is interesting.
Exactly.
So what is known about this representation theory, like structure of Verma modules and Katz determinant formula, something like that? Is it known? Was it studied?
So with Yassine Klef and a former student, Andrei Rotaro, we tried to do the S matrix. I mean, you can compute the characters. That's fine. And then you can try to see what the S matrix is and the fusion numbers. That's how we know what's here essentially.
Bantai was computing. Peter Bantai was working with
Yes. So actually, Peter Bantai also did that in a more general case.
He looked at orbifold by more general permutation subgroups.
Yes, so just
Okay.
Subgroup
In a way,
of
this is
permutation, not
the
necessarily
simplest case of it.
And for the Verma module, well, there's one case that's easy is if you are in the twisted sector, because the Verma module is isomorphic to the one of
Yes.
And I think they're not that complicated actually.
Essentially, this paper by Borisov, Alpern, Schweigert classifies, if you start from a minimal model, they classify the representations of the replicated model.
Oh, there's more questions.
So can you repeat what is the difficulty in getting the ODs for the blocks?
Well, maybe it's illustrated here is, say you start from this, insert that in your correlation function. So typically you would say, well, L minus 3 act as a differential operator. L minus 2, L minus 1 also. L minus 1 cube good, but then you have that L minus 3 half. So if you just use this, that's going to give you a linear relation between different correlation functions. Well, a differential equation, but that you get a system of differential equation between, well, for instance, you're going to have that one, but you're also going to have that one. But you need to get rid of this at some stage to just get an ODE for the first one. Otherwise, what you get is a system of differential equation. And sometimes it's enough if you have, but then you need different. So maybe that's fine if you have a system of 2 by 2 and you can solve it like that, but it's not always clear that you get enough differential equations. If you're familiar with maybe the W algebra case, it's the same kind of problem that you have all these W modes and you need to get rid of them because they don't act geometrically on.
There are no further questions. Let's thank Benoit again.
Vers des buffets à des cathédrales.